Hello, we are Hyunjun and Gona from the Department of System Semiconductor. In this video, we are going to introduce two digital logic projects, the counter and the finite state machine. Let's start with the counter. Before we introduce the counter, I'd like to explain positive edge triggered D flip-flop and negative edge triggered D flip-flop. PETDFF is built by connecting two D flip-flops in series. The first DFF receives an inverted clock, and second one gets a normal clock. As a result, PETDFF captures the input value D on the rising edge of the clock. In other words, when the clock goes high, PETDFF stores the current value of D into Q and holds it until the next rising edge. Any TDFF is almost the same, but the inverter is placed differently, like this. Because of this, any TDFF captures D on the falling edge of the clock. So whenever the clock is low, any TDFF stores the D value into Q and holds it until the next falling edge. Next, I will explain the divide by 10 to power of n up counter that I designed using PETDFF. Here is how it works. Among the 4-digit numbers, the least significant digit is implemented as a 4-bit counter. When it reaches 1010, which is 10 in decimal, it generates a pulse and reset to 0, like this. That pulse is sent to the next digit counter, increasing it by 1 every 10 cycles. Using this method, the circuit can count accurately in decimal. Let's take a look at the implementation video.
A few moments later.
Now I will explain the divide by 10 to power of n down counter, which is implemented using any TDFF. Its structure is same as PETDFF up counter, but I modified the code to perform down counting instead. Let's watch the implementation video.
A few moments later.
Finally, here is the 3 LED circuit, which uses these counters to create dynamic lighting effects. Let's see the implementation video.
Jingle bell, jingle bell, jingle bell rock. A jingle bell swing and jingle bells ring.
Now I will explain our FSM. First, our FSM has 8 inputs. There are a total of 6 buttons: the plus button, minus button, sleep button, reading button, normal mode button, and study button. We have a total of 12 states, with 3 brightness levels assigned for each mode, resulting in a total of 12 states. Pressing the plus button advances to the next brightness level, while pressing the minus button returns to the previous brightness level. Pressing the sleep, reading, normal, or study buttons immediately sets the state to the second brightness level of the respective mode. Like this. If no button is pressed, the state holds itself. This is the state table. It shows how the state transitions occur based on different inputs. Next, this is the overall structure of our FSM. We first designed the next state logic, then connected the resulting outputs to ETDFS. The output passed through the output logic and are displayed on the basis board. Now let's discuss the next state logic. We assigned unique 3-bit codes x2, x1, x0 to each of A inputs to avoid overlap. For the states, we assigned unique 4-bit codes Q3, Q2, Q1, and Q0, again ensuring no overlap by using gray code. The resulting next state values were designed as D3, D2, D1, and D0. After assigning the codes, we derived logical expressions for each D value using kernel maps, expressing these values in terms of Q and S. The resulting D values then feed into ETDFS, producing the Q values. Since we have 4 values, we need 4 ETDFS. These Q outputs feed back into the NSL, like this, thus completing the NSL circuit. Now here is the implemented video. Through this project, we studied and implemented PETDFS, NetDFS, and divided by 10 power n up and down counters. Additionally, we designed an 8-input, 12-state FSM. This concludes our presentation. Thank you.
Thank you.